Go to the cloud. So, the chapter 25 homework is due on the 15th. The chapter 26 homework is due on the 27th. We will have a review of chapters 25, 26, and 27 on the 27th. And our exam on chapters 25, 26, and 27 will be on the 29th. Or that's when it's scheduled. So we finished up chapter 26. We're starting chapter 27 on optical instruments. So various optical instruments combine mirrors and lenses and such to perform useful activities. So here, for example, is a microscope, which magnifies small objects using a couple of lenses. So we'll start with the human eye and the camera. Then we'll look at lenses in combination and corrective optics, like glasses. Then we'll do simple optical instruments. We'll start with the magnifying glass, then we'll move on to the compound microscope. Then we'll talk about telescopes and lens aberrations. So, the human eye is a device, is a structure where you have a lens and the retina at the back, and light is focused through the lens and an image is formed on the retina in the back. The light passes through the cornea of the human eye and gets focused on the lens by the lens on the retina. So this is effectively a series of lenses. And then the ciliary muscles here change the shape of the lens so it can focus at different distances. And the vitreous and aqueous humors inside the eye are transparent. And at the retina, rods and cones convert light into electrical impulses, which travel down the optic nerve and into the brain. The eye will produce, because it is a converging lens, it will produce a real inverted image on the retina. And the reason things don't look upside down to us is because our brain adjusts the image to appear properly. Our brain corrects for the fact that the image that forms is real and is inverted. But you could observe this. So like if the top of your eye gets poked, you'll see a signal on the opposite side kind of thing. And the ciliary muscles will adjust the shape of the lens to accommodate near and far vision. So the situation here is that your image distance is fixed, but you have a changing object distance. So you have to adjust the focal length. That's how you can focus images at different locations. So you adjust the lens shape to change the focal length of the lens to keep the image distance fixed on the back of your retina while being able to see different objects. Now, the near point is the closest point to the eye that the lens is able to focus. For normal vision, it's about 25 centimeters from the eye, but it increases with age as the lens becomes less flexible. Let me see, 25. And it's smaller when you're younger. Yeah. So, and the far point is the furthest point at which the eye can focus, and it's infinitely far away if your vision is normal. So here we have a problem. The near point distance of a given eye is 25 centimeters. Treating the eye as if it were a single thin lens, a distance of 2.3 centimeters from the retina, so that would be DI. Find the focal length of the lens when it is focused on an object at A, the near point, at 25 centimeters, and B, a DO of infinity. So typical values for the effective lens retina distance will range from 1.7 centimeters to 2.5 centimeters. So I will give you a few minutes to work this out. So thin lens formula, 1 over DO plus 1 over DI equals 1 over the focal length. We know DI, that's 2.3 centimeters. At the near point, DO is 25 centimeters. So we can plug those numbers in. 1 over 25 centimeters plus 1 over 2.3 centimeters equals 1 over the focal length. So 1 over the focal length is 0.47 inverse centimeters. And the focal length is 2.1 centimeters. Now, at infinity, DO, if we let DO go to infinity, then this term, 1 over DO, goes to 0. So 1 over infinity is 0. So 1 over 2.3 centimeters equals 1 over the focal length. So the focal length is 2.3 centimeters. Now, a camera is very similar to the eye. It has a lens and a film and a light type box. The difference is that instead of because the lens is, you can't change the lens. To focus a camera, instead of changing the focal length, you have to change the DI, the image length. You have to move where the image focuses. So for a camera, for your eye, you vary the lens and change the focal length. For a camera, the focal length is fixed because you can't change the lens. So you vary the distance between the lens and the film and change the image length. So the camera lens can't change shape. It moves closer or further away from the film in order to focus. And on cameras, the F number characterizes the size of the aperture. It's the focal length divided by the diameter of the aperture. And the combination of F number and shutter speed determines the amount of light that reaches the film. And then the sensitivity of the film is what's relevant after that. So F number is focal length divided by diameter of aperture. If the F number on a camera is increased, does the diameter of the aperture increase, decrease, or stay the same? So I'll give you a minute to think about that. So the F number is the focal length divided by the diameter of the aperture. So if the F number increases, the focal length doesn't change because the lens is fixed. So the focal length doesn't change as you can't change the lens shape. So what you're changing is the diameter of the aperture. And so if the F number increases, the diameter of the aperture decreases. So when you go to a higher f-stop, you are closing the aperture down. Now, you could also have a multi-lens system if you have two lenses. So in a two-lens system, the image produced by the first lens serves as the object for the second lens. So here we have an object. We have an object. It's producing an image for the first lens. That serves as the object for the second lens, which produces an image here. So to find the image formed by a combination of lenses, we have to consider each lens in turn, starting with the one closest to the object. And the total magnification is the product of the magnifications of each lens. So a nearsighted person has a far point that's a finite distance away. So objects further away will appear blurry. This is due to the lens focusing too strongly. So the image ends up formed in front of the retina. The solution here is you apply a diverging lens, which with a focal length such that a distant object forms an image at the far point. So if you had something at sort of infinite distance, this would form an image at the far point. And I think that for a very distant object, that makes the focal length be around where your far point is. So here, you have a nearsighted person. They have a far point that's 232 centimeters from their eye. if the lens in a pair of glasses is 2 centimeters in front of this person's eye, what focal length must it have to allow her to focus on distant objects? So we want to successfully form an image on the back of the eye. So we want to form an image formed by the concave lens should be at the far point of the lens. And then the distant object is some very large. So I'll give you a minute or so to think about that. So 1 over DO plus 1 over DI equals 1 over the focal length. Here, DI is going to be negative 321 centimeters because you're 2 centimeters in front of your eye. And you want to create an image at the far point. So negative, and DO is infinity. So 1 over infinity plus 1 over minus 221 centimeters is 1 over the focal length. So the focal length is 1 over is negative 321 centimeters. Basically, you want your focal length of your corrective lenses to be at your far point. And the strength of corrective lenses is usually quoted as a refractive power, which is the inverse of the focal length. And the units are diopters, which are inverse meters. So that 321 centimeters, that negative 321 centimeters would be 0.31 diopters. So that was for nearsightedness. For farsightedness, a person who's farsighted can see distant objects clearly, but can't focus on close objects. The near point is too far away. And the lens of the eye is not strong enough, and the image focuses behind the retina. This happens as you get older. Your lens gets stiffer, your muscles get weaker. It's harder to bring it into the case to focus on the near point. So for this, the corrective lens is a converging lens. And it brings the final image past the near point. So the object is inside the near point, and the image formed by a convex lens brings it out beyond the near point. Oops. So Bill and Ted are on an excellent camping trip when they decide to start a fire by focusing sunlight with a pair of eyeglasses. If Bill is nearsighted and Ted is farsighted, should they use Bill's glasses or Ted's glasses, or will either pair of glasses work just as well? Which of the following is the best explanation for your prediction? You use Bill's glasses because they're concave, which means they will focus light from the sun to a point. Use Ted's glasses because they're convex, which is the correct type to focus light from the sun to a point. Or either pair of glasses will work just as well because they both work by focusing light to a point. And as I was showing earlier by accident, the correct answer is to use Ted's glasses that are convex because they are the correct type to focus light from the sun to a point. Bill's glasses are concave and diverging, so they'd spread the light out. So a simple magnification device is a magnifying glass. It's a simple convex lens, and working in conjunction with the eye, it makes objects appear bigger because it makes them appear closer. Similarly to a corrective lens for farsightedness, it brings the near point closer to the eye. The angular size of an object is the angle it subtends on the retina, and it depends on both the size of the object and its distance from the eye. So the angular size of an object is going to be, so if it's far from the eye, it's going to have a smaller angular size. If it's closer to the eye, it'll have a larger angular size. And that angular size is going to be the inverse tangent of the size of the object over the distance. And if it's a small angle, you can use the small angle approximation, and theta is approximately h naught over d naught. And if the object is moved closer to the eye, its angular size increases. And if placed at the near point, its size will be h naught over the near point. So this is approximation. The exact value would be, tangent of theta equals h naught over d naught. Actually, it might be sine of theta. Well, for small angles, tangent and sine are the same. But yeah, it's tangent of theta is h naught over d naught. But for small angles, that's approximately h naught over d naught. So if the object gets moved closer to the eye, its angular size will increase. And if it's placed at the near point, its size will be h naught over the distance to the near point. But if you place a converging lens whose focal length is less than the near point length, very close to the eye, and if you put the object at the focal point of the lens, this will give the object a larger angular size. The image will actually end up at infinity, but most importantly, it will be bigger. The angular magnification, the maximum magnification with a magnifying glass, which is theta prime over theta, ends up being h naught over the focal length divided by h naught over n, which is n over the focal length of the lens. So the magnification can then be maximized if you have the image at the near point. Instead of having the object at the focal point of the lens, you can futz around with things and put the image at the near point and get maximum magnification. So if the image is at infinity, magnification is n over f. If the image is at the near point, it ends up being at 1 plus n over f. So a person with a near point distance of 26 centimeters examines a stamp with a magnifying glass. If the magnifying glass produces an angular magnification of 4.0, what is its focal length? So there's two ways you can do this. It's assuming your image is at infinity. Magnification is n over f. Focal length is going to be n over m, 26 centimeters over 4.0. And so the focal length will be 6.5 centimeters. However, you could have a situation where you adjusted things to put the image at the near point, wherein magnification is 1 plus n over f. The focal length ends up being n over a magnification minus 1, 4.0 minus 1, and you get 8.667 centimeters. Let me make this a little clearer. So, So if the image is at infinity, the focal length will be 6.5 centimeters. If the image was at the near point, you have a focal length of 8.67 centimeters. And where are we? Well, I'll quickly go over the microscope, but I think that'll be the last thing we cover since so few people are here and we're ahead of schedule anyways. So a compound microscope in its simplest form has two converging lenses. One, the eyepiece is close to the eye, while the objective is close to the object. The object is placed near the focal point of the objective lens, giving a magnification of minus di over do, which is approximately minus di over the focal length of the objective. And the image is formed at the focal point of the eyepiece, which produces an image at infinity. So the magnification of the eyepiece is n over the focal length of the eyepiece. And so the total magnification is given above and is the product of the magnification of each lens. It's minus di n over focal length of the objective times focal length of the eyepiece. And so if you have a near point distance of 225 centimeters, and you're using a microscope to view an amoeba, the objective has a focal length of 1 centimeter, the eyepiece has a focal length of 2 centimeters, and the amoeba has 1.1 centimeters from the objective. What's the magnification of the microscope? So the eye here is the image formed by the objective. That is the length of the microscope minus the focal length of the eyepiece. The magnification is going to be di minus di over focal length of the objective, and focal length of the eyepiece. So we need to find di. We know do and the focal length of the lower thing. So that's 1.1 centimeters. 1 over 1.1 centimeters plus 1 over di equals 1 over 1.0 centimeters. So di ends up equaling 11 centimeters. So we can plug that in. Minus 11 centimeters over 1 centimeter times n, 25 centimeters over 2.5 centimeters. Ends up being minus 11 times 10, so minus 111. And I think I'm going to stop there for today. We will continue with this on Wednesday because we are ahead of schedule. And yeah, I'm going to stop sharing. And